classifying and categorizing and giving names to the types of stars is a helpful way to start understanding how they behave and understanding essentially the community of stars that are in our night sky. We've talked a little bit about classification already with the OBAF-GKM scheme that was devised by Annie Cannon. That taught us that it's helpful to think about stars in terms of their temperature, and that their temperature is directly connected to their light spectrum and the color of the star. And so now we have spectral types of stars. But there are other properties of stars that we're interested in, and so building on that, we're going to talk about a special diagram called the HR diagram, and that will help us think about the community of stars, where a particular star falls on that diagram will be directly related to what type of star it is, and hopefully will help us get a grasp on what types of stars are out there. Okay, so in the last video we were talking about binary stars, and so that gave us a way to understand the mass that stars have. So once you have a relationship for the mass of a star, you can start comparing the mass to other properties that you can observe and see if there's relationships there. And a very clear relationship that emerges is between mass and luminosity. And maybe this isn't so surprising, but the most massive stars are also the most luminous. If they're more massive, they're producing more light. And this plot shows this really clearly. You increase the mass of the star, you increase the luminosity of the star. Now, it looks like a straight line here, but this is not a linear relationship. If you'll take a look at the axes, you'll notice that this is not linear. These are logarithmic. So in the luminosity axis here, each tick mark is 100 times bigger than the previous one. The ranges in luminosity of stars are just enormous. So the sun would be here with a luminosity of 1 and a solar mass of 1. And so the luminosities increase 100 times each time you go up one tick mark. So a star here is now 100 times more luminous. And that luminosity is directly related to how much mass it has. Okay, now this is sort of a logical relationship. It's not meant to be mind-blowing or anything. But we can look at lots of relationships in this way. Now, for example, with humans, you could look at the relationship between their weight and height. Right now, there's lots of factors that affect your weight or your other physical properties. But if we look at this relationship, you would get what you would expect, that heavier people tend to be taller, right? You just have more person there. Now, this graph is plotted sort of in a backwards direction. So if you notice the arrow here, weight is going this way. So these are the heavier people, and these are the taller people. And you'd see a pretty nice, neat relationship between these variables. But it wouldn't be perfect, right? Mostly, it would agree with what you expect, but there would be some heavier people who are not very tall, and there would be some light people who are very tall, right? So there's going to be groups off of the main line here. Okay. Now, thinking about this graph in this picture is really an analogy. It's an analogy to what we're going to look at for stars in the next graph. So this is the HR diagram that I was referencing. H and R stand for the two inventors of the diagram, Hertzsprung and Russell. And what they found is that when you look at the temperature and the luminosity, and for sort of historical reasons, they plot the temperature in reverse. You get a really interesting relationship, and it looks very similar to the weight and height graph that we saw before. So this is what the HR diagram looks like for a large collection of stars plotted. There's a clear trend where the hotter stars over here are more luminous and the cooler stars are less luminous. Again, not mind-blowing. This is what you would expect, that hotter means brighter, just like more massive means brighter. But it's not a perfect relationship. There's some scattering going on, and off of the main line, which is called the main sequence, you have groups of stars. So these stars are clearly, there's something different about these stars here than the ones that are along the main sequence. These stars are very bright, they're high in luminosity, but they're relatively cool. And then there's another group down here. These are hot stars, but they're not very luminous. All right, so we're going to look more at this HR diagram. We've talked about how this is the main sequence, and what characterizes stars on this line is they are burning hydrogen in their cores. Now you might think, well, don't all stars burn hydrogen in their cores? Yes, at least for a time they do. But eventually, stars will reach a point where they run out of hydrogen in their cores, and that's when they move away from the main sequence. So stars will spend about 90% of their lives on this line. Now, so on this line, there's a specific relationship between how hot the star is and how much light it's producing. And all of these stars along that line are producing hydrogen. Once they burn too much, burn all of their hydrogen away, they'll start burning helium and then onto other types of nuclear fuel. At that point, the relationship between temperature and luminosity changes, and the size of the star changes, and it goes through an evolution. We're going to get into the details of that evolution, but for now, know that these stars that are off of the main sequence are no longer burning hydrogen anymore. Something has happened to them. They've evolved off of the main sequence. They've gone through 90% of their life somewhere along this line, and now they've moved on somewhere else onto the diagram. Okay, now the groups of stars on here are worth noting. The coolest stars are usually called red dwarfs. So they're small, reddish colored cool stars, not very bright. And there's a big population of those kinds of stars in the universe, although they're dimmer, so we don't see them very often. The red giants, on the other hand, are very visible when they're not too far from the sun anyway. And those stars will be in this part of the diagram. So red giants are another type of stars that we will encounter on a regular basis. Stars that are sort of in this range of the main sequence will go through a red giant phase after they've burned through their hydrogen. If a star is very, very big at the start, so it's a very high luminosity star to begin with, instead of becoming a red giant, it might become a red supergiant. And then if it doesn't drift far enough to the right, it could also be a blue supergiant and stay in this part of the diagram. Even later, stars will slowly change in some way, and many of them will become what are called white dwarf stars. We've encountered this briefly when we were looking at the difference between, I think it was a white dwarf and a supergiant, and how their spectral lines were different even though they were the same temperature, right? So you could have a blue supergiant here and a white dwarf here that are the same temperature, so their spectral pattern is the same, but the white dwarf would have slightly wider, blurrier lines because it has a higher pressure, because it's a more compact star. It's a smaller object. It's not very luminous at that stage, but it's still very hot. So the main parts of just to summarize this diagram, the main parts of a HR diagram are the main sequence, where the stars burn hydrogen, the red giant region, and the white dwarf region. And as we study stellar evolution, we'll understand how the stars go from one to the next a little bit better. Okay, so this table here is just for main sequence stars, and it includes a bunch of information about the properties of the various spectral types along the main sequence. Now you'll notice that there's some correlations here. Just along the main sequence, spectral type O, so these are your hottest stars, are also the most massive and the most luminous and the biggest, right? So these things are all correlated with one another. Along the main sequence, your hottest stars are the most massive, they're the most luminous, and they're the biggest in radius. As you move towards the type M stars, the coolest stars, you're finding stars that are much less massive, much less luminous, and much smaller in radius. So all four of these main variables here are interrelated for stars on the main sequence. Okay. Now, the range in sizes of stars is really impressive. This is one of those cases where I can say it, but to see how the sizes vary is much more instructive. So I've linked here to a video by a visual effects artist who's put together a nice sort of sequence of different sized objects, taking you out to the biggest stars, so you can see to scale how one star compares to the next. And I think it's really, really well done. So I'd encourage you to watch through this, and you can see how you go from one size to the next, and how stars that are on the large end of the spectrum really do dwarf even the sun, which we've already come to understand is a very, very large object compared to the things that we're familiar with, like the Earth and the Moon. But to illustrate that, at least in one picture, here we have one of the largest known stars, VY Canis Majoris, and this dotted region is the orbit of the Earth. And so when you zoom in there, you have the orbit of the Earth, you'd see the size of the sun here at the center. The sun is basically like a single pixel in the picture of this one star. On the other end, when you get to the really, really small stars, stars can be much smaller than the sun. For example, the white dwarfs, coming back to those stars. White dwarfs are only about the size of the Earth. So the sun can be like a speck of dust to the largest stars in the universe, and the smallest stars are like a speck of dust to the sun. There is one white dwarf star that maybe you can't see it, but you can see where it is in the night sky when you find the star Sirius. The star Sirius, which is one of the brightest stars in our night sky for part of the year, it is actually a binary system, and its binary companion is a white dwarf star. Now, as I was saying, you can't see the binary companion, so if you look at Sirius up in the sky, you won't see two stars there. But you can know that there are two stars there, and that second one is a white dwarf. So one is like a bright blue star, so it's very, very large, massive star, and then the other one is a white dwarf. Now, if you have a very powerful telescope in visible light, you might be able to see that binary companion, that white dwarf star. So this would be the white dwarf star right here. And so it's called Sirius B, and this is Sirius A. In visible light, this is what you would get. If you switch over to X-ray, you'd find that this white dwarf is actually putting out a ton of X-ray radiation. And so this is the image of those two stars in X-ray. And in X-ray, Sirius B is actually much brighter because this is an incredibly hot object. It's not producing a ton of luminosity, but it is incredibly hot. And so looking at the different spectrums reveals that difference. Okay, but white dwarf stars are sort of the small end of what stars can be. Then we have the blue supergiants and the red supergiants on the other end of how big stars can be.